Welcome back, 8th grade. The fundamental counting principle. These aren't too bad, but we do have to think. All right, you guys are pretty good at that, and hopefully you're up for the task. All right, an experiment consists of rolling a fair numbered cube with faces 2, 4, 6, and 8, 10, and 12. Find each probability. Rolling an even number. So, an example is a cube, and they're all even numbers. So there's 6 that are make what we want. Out of 6, that would be 1. Because 6 of the faces met even numbers, and there were only 6 faces. So 6 over 6 is a 1. Rolling a prime number. Now in these, I know 2 is a prime number. That 1 meets my requirement. The other 5 are not. So there's 6 total choices, and one of them meets it. It's 1 over 6. Rolling a number greater than 7. Greater than 7. Greater than 7, greater than 7. 3 of them meet my requirement. 6 total choices, so 3 out of 6. Or 1/2. I went to lots of extra trouble to put all the different variations of 1/2 or whatever it may be for an answer that could be possible. Please do reduce, but if you don't, you still have a chance at getting it right. All right, problem of the day, 45. Learn to find the number of possible outcomes in an experiment. Fundamental counting principle and tree diagram. These are drawings. Drawings do help a lot of the time. If there are m ways to choose a first item and n ways to choose a second item, after the first item has been chosen, then there are m times n ways to choose all the items. Multiplication. Oops, lie. If things happen consecutive in order, we know we need to multiply. That is important. This is multiplication when there's multiple steps. Okay. License plates are being produced that have a single letter followed by 3 digits. All license plates are equally likely. Find the number of possible license plates. So we have to think. There's a letter. Then there's 3 digits. For the letter, that could be 26 different things, right? Because there's 26 letters in the alphabet. We have the number, we have the number, we have the number. Remember, these are all single digits. Now there are 10 single digit numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. 1 through 9 is 9 of them, and then don't forget about 0. So there could be 10 different number choices. There could be 10 different number choices for that one, and there could be 10 different number choices if they're all likely equal. So we figured out how many different possibilities for letters, how many different for each number, and now since they're happening in a row, we multiply. 1,000 times 26, 26,000. Oh, there are 26,000 different license plates possibilities because of what we know. Let's see if they come up with the same thing. Use the fundamental counting principle. They gave us 4 spots on the license plate. Letter, first digit, second digit, third digit. There are 26 choices because there's 26 different letters. 10 choices because there's 10 different single-digit numbers. 10 choices because there's 10 single-digit numbers. And again, 10 for the same reason. We multiply all those and we get, there are 26,000 different possibilities. We got the right answer. The number of possible 1-letter, 3-digit license plates is 26,000. Find the probability that a license plate has the letter Q on it. So, the same license plate situation where we have letter, then we have number, number, number. Does it matter that we have whatever number? So, every number is a desired and every number is there. Because it doesn't matter what number we have, so that's a 10 out of 10. Because if I get a 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0, it's right. It doesn't matter what the numbers are. That's why we can say that 10 of the 10 numbers fit. But with the letter, there's 26 of them total. How many certain letters do we want? We want that Q. There's only one letter that meets that, 26. So the numbers didn't matter, so we put 10 over 10 for each of them. The letter did matter. We have to have that specific letter. So 1 out of 26 chance of getting that letter. So we do our multiplication. 1,000 on the top, because 1 times 10 times 10, and 26,000 on the bottom. I'm going to go ahead and say, oh, divide by 1,000, divide by 1,000. Our chance is 1 in 26 of getting a license plate with a letter Q on it. Let's see if we're correct. All right, probability of Q and 3 numbers. All right, oh, there's 1 over 26, 10 over 10, 10 over 10, 10 over 10. We already knew that that was 26,000, so that's what they did. When they multiply it out, it's approximately 1 over 26 because they reduced already. I like to look at each individual thing, and I like it a lot better when they write, oh, 1 over the 26, because 1 Q out of 26, 10 out of 10 numbers, because, yeah, doesn't matter what number we have, 10 out of 10, 10 out of 10. Hopefully you can see, oh, these 3 multiply to make that, and those 3 are what they have on top, or 4 are what they have on top. It is the same thing. When they write it this way, though, I think you lose some of that context. So what we did the first time is what they did. It's just they went ahead and took the liberty of multiplying that for us. And it's about 1 out of 26, or 0.38, or 3.8%. So not a real great chance of getting a Q. Okay. Find the probability that a license plate does not contain a 3. Okay. So we've got our letter, we've got our number, we've got our number, we've got our number. Now we know there's 26 letters and 10 of every number. I'm starting to think like that already. Does it matter what letter we have? The letter doesn't matter, so the letter really could be anything. So 26 out of the 26 meet that, right? Not a 3. Is it okay if it's a 0, a 1, a 2, a 4, a 5, a 6, a 7, an 8, and a 9? Oh, so 9 of them are okay. That 1, that 3 is not. The number 3 is not okay, but the other 9 are okay. So 9 out of the 10 are okay. Would it be the same thing here where 3 is not okay, the others are all okay, so 9 out of 10 and 9 out of 10. When we do that multiplication, we get 26,000 on the bottom. And then whatever 9 times 9 times 9 times 26 is. Let's go ahead and see. And they went to a decimal. You can go to a decimal or a percent, or you may leave it as a fraction, but please do reduce if you can. All right, so let's use that counting principle. Oh, 26 out of the 26, we're fine. 9 out of 10, 9 out of 10, 9 out of 10. Oh, so that number over 26,000, because there's your 9 times 9 times 9 times 26, 18,954. Oh. All right, we put that in there. And the probability of not getting a 3 is around 72.9%, or 0.72, or we leave it as this fraction. I think decimals are really easy to represent. If you like to change them to percent, that's fine. I've tried to list it all 3 ways in the answers, but I'll check them all no matter what. All right, let's move on. Find the number of possible Social Security numbers. Your Social Security number has 9 digits. There are 9 different numbers. So, how many different possibilities are there when we have that? Oh, there's 10 different single-digit ones. All of these have that possibility of 10 different numbers. When we look at all those together, we would get 10 to the 9th power, or they'll show you how big and long that number is. All right? Because each one of these individual spots could have 10 different numbers. That's why they each get a 10. Okay. For the first spot, you could have a 10. 10 different options. Second spot, 10 different options. Third spot, 10 different options. And so on down the line. When we multiply all those, we get 1 billion different options. All right? With these 1 billion different options, that should be enough to provide for most of us. The number of Social Security numbers is 1 billion. What is the probability that the Social Security number contains A7? Contains 1 7. Not contains a bunch of sevens, not contains 3 sevens, but contains A7. Oh my. Well, we have to think about each of the spots. We only need one of the spots to contain a 7. So one of them has to have a 7. It's a 1 out of 10 chance. The rest of them, the other 8, if you count these, it doesn't matter what they are, so we put them as a 10 over 10. And therefore, when we do this multiplication, because one spot needed to have a 7, so that was 1 out of 10. The rest, it didn't matter, so that was 10 out of 10. All right? When we do that, oh, excuse me, it would be 100 million over 1 billion, and you do that division, it becomes 1/10. All right? Because essentially what happens here is we have 100 million. They kind of take a leap here because they're math people. Do you see how if I divide by 100 million, I get 1. If I divide by 100 million, I get 10. Oh, 1/10. So they just simply reduced. There's all they did. Okay. Find the probability that a Social Security number does not contain a 7. Now this one's going to be different. What's the possibility of it not containing a 7? So again, like before, no 7 means 1, 2, 3, 4, 5, 6, 8, 9, 10. Those all work. But that 7, no. So we're going to get a 9 out of 10 because no, that 7 can't be. And all of them have to be 9 out of 10s. All right? When they multiply that out, that means you get 387,420,489 over 1 billion. So there are that many numbers without a 7. That's about 40%. Okay? We have to think about each situation. Can't be a 7, so 9 out of 10. Can't be a 7, so 9 out of 10. Can't be a 7, so 9 out of 10. They just save you that trouble of multiplying all the 10s together to get 9 billion. Okay? The fundamental counting principle tells you only the number of outcomes in some experiments, not what the outcomes are. A tree diagram is a way to show all of the possible outcomes. So we can still figure out how many of the outcomes there are with our counting thing, but we can't figure out what all the matches are. So they're going to show us some problems. You have a photo that you want to mat and frame. You can choose from a blue, purple, red, or green mat. So we can have a blue, purple, red, or green mat. Okay? And a metal or wood frame. Okay? A metal or wood. A metal or a wood. A metal or a wood. A metal or a wood. Okay. Describe all the ways you could frame this photo with one mat and one frame. Well, I could have a blue with metal, I could have a blue with wood. Purple with metal, purple with wood. Red with metal, red with wood. Green with metal, green with wood. So I see that there's, if you look at that bottom line, 8 different ways. All right? Oh, this shows all the different possibilities. Not only how many there are, but all the different possibilities. So, you can find all the possible outcomes by making a tree diagram. There should be 8 different ways. We saw that from before because there were 4 possibilities of colors, 2 of frames, types. 2 times 4 is 8. Hey, we came up with that. And our photo. We could have a blue with metal, blue with... Hey, that looks pretty familiar, doesn't it? Each branch of the tree represents a different way to frame the photo. The ways come in the branches could be written as blue metal, blue wood, purple metal, purple wood, red metal, red wood, green metal, green wood. And those are our 8 choices. We can still do probability stuff with those. Let's see. So a baker can make yellow or white cakes. We can have yellow. We can have white. With a choice of chocolate, strawberry, or vanilla icing. Ooh, chocolate, strawberry, vanilla. This one can be chocolate, strawberry, or vanilla. Okay. Describe all the possible combinations of cakes. Okay. So, I see at the bottom here there's 6 different things. I could have yellow chocolate, yellow strawberry, yellow vanilla. White chocolate, white strawberry, white vanilla. 6 different ones. Or if I thought about that counting principle, 2 different types of cakes, 3 different types of frosting. 2 times 3 is 6. Okay? And we have all the possible things by writing out this diagram. Okay? Yellow with chocolate, strawberry, vanilla. White with chocolate, strawberry, vanilla. And we see the 6 different possibilities. Now, there are 7 black socks and 2 white socks in a drawer. 2 socks are removed. What is the probability that the colors match? This is one of the ones that is, you got to think a little bit. So, the other day, we had that marble bag and we drew into it and didn't replace. So it changed what the outcome was. So let's think. How many total socks are in the drawer? I see 7 black, 2 white. That means there are 9. Now, if I want to get black socks, that first time I draw it, there's a 7 in 9 chance of getting a black sock. Okay? That second time, there's only 8 socks left in the drawer. And I removed one of the black socks, so there's a 6 in 8 chance of doing that. Now, I'm going to reduce before I multiply. Oh, that was not what I meant to do. This will become 3. This will become 4, divided each by 2. Then this will become 1. This will become 3. I divided each by 3. So I get 7 out of 12 for my chance of getting black socks. Now for white socks, that first time there's a 2 out of 9 chance. Okay? That second time I've already drawn, so there's 8 socks left and only 1 white sock left. There's a 1 out of 8 chance. Now I am going to reduce before I multiply. That becomes a 1, that becomes a 4. 1 out of 36 is my chance for getting that. So I have a chance of getting this, a chance of getting that, but it wants to know the chance of either or happening. Since either or can happen, we have to add them. So I'm going to multiply this by 3 over 3, 21 over 36. Do you see that now has the same denominator as that? We can add them then. And then we have the 1 over 36. This happening or that happening means we add. 22 out of 36 is the chance, or we can think 11 out of 18 is our chance of getting a pair of socks that match. Let's go ahead and look at their math. Okay. We have to look at black socks. 7 out of 9 for that first one. 8 choices for socks are left. All right, so then there's 6 out of 8, or 3/4 for that second choice. Oh, first choice 7 out of 9, second choice 6 out of 8. We did that. All right, 2 out of 8, or 1/4 chance of the white socks. Okay, 7 out of 12 of getting a black sock. That's what we got. Now with our white sock here, we have a 2 out of 9, and we have a 1 out of 8. All right? We have a 1 out of 36. The pair is what we wanted, so I focused on that. The pair is what we wanted, so I focused on that. This or this happenings means we add the two together. So we add those together, we get 11 out of 18, and 61 is our choice. All right, there are 5 black socks and 3 white socks in a drawer. 2 socks are removed. What is the probability the socks will match? So for our black socks, we have a 5 out of 8 because there were 8 total socks. Yay, we get the sock that we want. Now we have a 4 out of 8 chance, or 4 out of 8, there's another way of writing that, 1 out of 2. There's a 5 out of 16 chance of getting a black sock. That's one of the possibilities. For our white sock, there's a 3 out of 8. Yay, we get the one we want. Now we have a 2 out of 7 chance. I made a mistake. We'll come back to it. Hopefully you saw it. All right, so 2 out of 7. I'm going to reduce 1 and 4. 3 out of 28 chance of getting a white sock. Here's what I messed up the first time. I got that black sock, so there's only 4 of them left, but I forgot to reduce that number. All right, I'm going to reduce 1. That becomes 2. 5 out of 14. So I have my black socks, I have my white socks. I'm going to do 2 times 2 to get a common denominator. So 10 out of 28, or 3 out of 28, because this one we're going to have to add in. The 3 out of 28 is 13 out of 28. It's a little less than 50% chance of getting a pair just randomly drawing. And that's why so many of you wear different colored socks every day. All right, so let's go through. They're going to make their picture. I only focused on this route, which will be the top up here. And they came up with 5/14, as did we. All right, and I'm only going to focus on the 2 white socks together. It's 3/28. Then we have to add the 5/14 and 3/28. We get 13 out of that, and that's 46%, roughly. One other thing that I do want to point out, many times there are 3 options, like in a meal. So in a meal, I could have pork, I could have beef, or I could have chicken. So these are my meal choices. They all go back to the meal. Then I could have a potato, I could have a baked potato, or I could have noodles. Okay, so all of them, potato, baked potato, noodles. Potato, baked potato, noodles. Okay? Then in that third one, if I had a pork chop with a potato, I could have carrots, I could have green beans, or I could have broccoli. And with each of these, I get 3 options. Carrots, green beans, broccoli. Carrots, green beans, broccoli. And if I go through, I end up with 27 things on the bottom. 3 choices first round, 3 choices second round, 3 choices the other round. And it shows me 27 different possibilities. You can do this in more than 2 levels like they showed, and you'll be expected to. So, ask me if you have those troubles.